I'm William Moses, and I'll be presenting our paper, Instead of Rewriting Foreign Code for Machine Learning, Automatically Synthesize Fast Gradients. Computing derivatives is key to many machine learning algorithms, such as backpropagation in neural networks, Bayesian inference, and uncertainty quantification. Existing approaches require the user to rewrite all code in a differentiable DSL such as PyTorch or TensorFlow, or to manually write all of their gradient functions. Such rewriting can be both difficult and time-consuming, requiring the ML researcher to spend time understanding how the library they want to use is implemented rather than using it to solve their actual research problem. This hinders the application of ML to new domains, as many programs, such as physics simulators and climate models, are not already written in ML frameworks. As a result, the community has started creating tools to automatically synthesize gradients of foreign code. Conventional wisdom dictates that automatic differentiation is only feasible at a high level. This stems from the need of high-level semantics to run the automatic differentiation algorithm and the belief that without high-level information, the performance of AD will be greatly hindered. As a consequence of this conventional wisdom, we have a variety of different tools that each operate on an individual source language, thereby ensuring that the tools have access to the high-level information. These tools then produce a gradient in the original source language, which is later lowered and optimized by traditional tools. Enzyme overturns this conventional wisdom by demonstrating an automatic differentiation tool that works on a low-level representation and achieves state-of-the-art performance. This allows Enzyme to act as the best of both worlds, enabling differentiation on and between a variety of languages while maintaining performance. In fact, in contrast to existing tools, Enzyme can differentiate after optimization, which enables a 4.2 times speedup on a standard benchmark suite. Finally, Enzyme demonstrates the ability to derive all the necessary semantics to perform AD at a low level. Enzyme computes derivatives of programs in the LLVM intermediate representation. LLVM can be thought of as a cross-platform assembly that is used by a variety of front-end languages, such as Julia, C, Rust, Swift, TensorFlow, and many more. Its operations have well-defined semantics and a large suite of optimizations and analyses for improving the performance of code. Let's see the impact of these optimizations in practice. Here we have two functions, mag and norm. Mag computes the magnitude of a vector in O of n time. Norm normalizes a vector in O of n squared time by calling mag n times inside a loop. By running an optimization known as loop invariant code motion, we can move the call to mag outside the loop and achieve an O of n runtime. Performing AD on this optimized code, we find a gradient that also runs in O of n time, as the call to the gradient of mag is also outside the loop. Instead of first performing optimization, then AD, let's see what happens if we first perform AD as is done in the existing tools. We again start with an O of n squared program, and running AD on it yields an O of n squared derivative, as the call to the gradient of mag is inside the loop. If we now try to optimize the derivative, we are unsuccessful and stuck with the O of n squared gradient. This is because the call to the gradient mag uses the variable dres defined inside the loop and thus cannot be moved outside. As a result, we find that differentiating after optimization can create asymptotically faster gradients. This is one of the key insights of Enzyme. By performing AD on a low-level representation, we can run after optimization. While it's now clear that low-level AD has several benefits, it also comes with additional challenges. Low-level code lacks necessary information for computing adjoints, such as the type of data being loaded or stored. This makes it impossible to naively perform AD on such a representation. To remedy this, we created new interprocedural analyses that are able to derive the relevant information for performing differentiation. Let's now take a look at how Enzyme works on a simple piece of code. At the top left, we have C code that computes ReLU of x cubed. We can request the gradient of this function as demonstrated on the bottom left by calling enzyme autodiff and passing the function to differentiate as the first argument. To the right, we have LLVM that represents our ReLU3 function. It first compares if x is greater than 0, and if so, computes x cubed in con.true. Otherwise, it branches to the end and returns 0. Enzyme begins its differentiation process by analyzing the input program. Here we highlight the results of activity analysis, which detects which instructions and values could impact the gradient computation. Here, the active values include the argument x, the call to pow, and the final value being returned. Enzyme then allocates and zeroes a new shadow location for all active values. which will store the current derivative of that value. Enzyme then creates a copy of every block in the original program to compute the gradients, known as the reverse pass. For every active instruction in the original code, outlined in red, Enzyme will create a corresponding adjoint that propagates derivative information. For example, on the left, we see Enzyme computing the adjoint of the x cube instruction. In the corresponding reverse block, we add instructions that increase the derivative of x by 3x squared times the derivative of the call. Finally, optimizing this, we find that something looks quite clean and is essentially the optimal handwritten gradient. We benchmark Enzyme on an extended version of Microsoft's machine learning-focused AD Bench suite, adding in 3 technically interesting programs. The Enzyme pipeline first runs a round of optimization, then Enzyme AD, and a final round of optimization. The reference or ref pipeline first runs Enzyme AD, then 2 rounds of optimization. This emulates existing systems where AD must be run prior to optimization. This allows us to run an ablation analysis where we compare the impact of optimizations on AD without any conflating factors. Finally, we compare the fastest 2 tools benched by AD Bench, Topinot and Adept, followed by 2 rounds of optimization. Here we plot the speedup of all the tools, with the value of 1 being the fastest. We find that Enzyme is 4.2 times faster than ref on average, and at least as fast as all other tools. Looking at the differences between Enzyme and ref, we see that most programs have a sizable speedup for Enzyme. The last 2 tests, FFT and Brussels Radar, were already highly optimized before LLVM, making the Enzyme and ref pipelines equivalent. From here, we can also evaluate how Enzyme compares with existing tools. Looking at the LSTM and bundle analysis tests, we see that Topinot's performance is similar to the reference. This implies that Enzyme speedup over Topinot in those benchmarks comes from its ability to run optimizations first. For the other experiments, the reason for the performance gap is more nuanced. Enzyme uses a different data structure to cache values, which is also partially responsible for the performance gap. In fact, Adept must keep a dynamic tape of what instructions were evaluated in the forward pass to be able to run its reverse pass. In contrast, Enzyme statically compiles everything ahead of time. Finally, Topinot has a red X on the Euler and RK4 tests, as it does not support C++ code. In conclusion, we present Enzyme, a tool for performing reverse mode automatic differentiation of statically analyzable LLVMIR. This allows Enzyme to differentiate programs in a variety of languages and allows Enzyme to perform AD after optimization. Enzyme achieves a 4.2 times speedup over AD before optimization and achieves state-of-the-art performance when compared with existing tools.